February 18, 1943. Boeing Field, Seattle. Inside the cockpit of the Boeing B-29 Superfortress, test pilot Eddie Allen grips the control column. The airspeed needle trembles. The engines growl low but uneven, each combustion pulse echoing through the thin metal frame. The runway slides forward too slowly, as if the ground itself were resisting. Heat builds inside the cockpit. The smell of oil and scorched metal mixes in the air. Breathing becomes shallow, deliberate. The aircraft accelerates. Pressure tightens across the chest. Pale winter light reflects off the oversized wing roots. As the nose wheel lifts, a violent shudder ripples through the fuselage. The sound changes, not the surge of power, but something wrong, unspoken. Altitude increases, but reluctantly. The runway is gone. The edge of the city appears at the far end of the windscreen. For a few suspended seconds, the aircraft hangs between flight and collapse. There is no margin left, no time to correct. Only lift, wait, and a decision that must be paid for immediately. This story does not begin on the battlefield, and it does not fail because of a lack of technology. It begins with a paradox that the most capable minds of the era were reluctant to face. A machine designed to carry war farther than anything before it could not leave the ground safely. The problem was not weak engines, nor human incompetence. Every individual specification was correct. Every calculation made sense. But when everything was forced together, under the same timeline, the same runway, the same political pressure, the system began to betray itself. This is not a story about victory, it is a colder question. What happens when a machine is right on paper but wrong in reality, and war refuses to wait for it to be fixed? To understand why such risks were accepted, the story has to move backward to a moment when delay was no longer an option. After the initial shock in the Pacific, the United States faced a strategic problem defined by distance. The enemy was far away. Forward bases were fragile. Existing bombers lacked the range, payload, and operating altitude needed to survive against modern defenses. A new program was pushed forward at unprecedented speed, not because it was perfect, but because there was no alternative. The pressure did not come from the military alone. Political expectations and industrial momentum amplified it. Thousands of factories were already being reconfigured. Production lines were taking shape while the blueprints were still changing. Time became the most dangerous adversary. If deployment was delayed, the war could stretch on for years longer, at the cost of hundreds of thousands of lives. If deployment came too early, before the system was fully proven, the risk would be transferred directly to those who flew and maintained it. In that environment, there were no clean choices. Not acting meant accepting strategic failure. Acting meant entering a gray zone where accidents were no longer hypothetical, they were anticipated. From conference rooms to factory floors to runways, the system chose to gamble, not out of recklessness, but because the war offered no permission to wait. At the center of the crisis was a number that seemed neutral, almost harmless: takeoff weight. Once fully loaded with fuel for transoceanic range, bombs for a complete mission, and a dense stack of pressurization systems, radar, and defensive armament, the aircraft exceeded what existing infrastructure had been designed to handle. On paper, lift was sufficient. In controlled tests, the engines met their rated power. But on real runways, aging concrete, fixed length, changing temperature, and humidity, small margins accumulated into lethal risk. The long, slender wing, optimized for high-altitude flight, demanded higher takeoff speeds. That requirement forced longer acceleration runs, while the available runway remained unchanged. A single engine lagging for a few seconds, or a slight shift in wind, could trap the aircraft in a dangerous state. Airborne, but unable to climb. Committed, but with no remaining ground to abort. Safety margins calculated for ideal conditions collapsed under the realities of mass production. The problem extended beyond aerodynamics. Distributed manufacturing meant each aircraft carried subtle differences in center of gravity. Fuel shifted unevenly during test profiles. Brakes and tires absorbed loads far beyond their original limits during high-speed aborts. Each component passed inspection in isolation. Together, the system became fragile. And because schedules could not slip, flight tests continued from runways that had not yet been extended. A silent compromise between engineering discipline and time. When extending runways could not be completed in time, the system was forced to look elsewhere. The solutions that emerged were not meant to make the aircraft better, only to make it able to take off at all. Weight was cut from places no one wanted to touch, armor protection reduced, non-essential equipment removed from early flights, fuel loads restricted during testing. Each decision was justified by spreadsheets, but what disappeared was safety margin, the one variable that never appears cleanly as a number. At the same time, operating procedures were tightened to an extreme degree. Pilots were required to follow precise speeds, flap angles, and split-second decision points for aborting or committing to takeoff. Instinct had no place here. Everything depended on discipline and on the hope that the next aircraft would not be the one where cumulative errors aligned. Maintenance crews worked through the night, adjusting engines and brakes, fully aware that a single deviation could turn the next rollout into disaster. At the management level, risk became an accepted component of schedule. Accident reports were not concealed, but they were weighed against charts showing how little time remained. The temporary fixes kept the program alive, but at a cost. A prolonged testing phase where every takeoff carried an unspoken question. How much longer could the system endure before something finally gave way? Within those numbers and procedures were people, but none of them were allowed to become the focus. Test pilots climbed into the cockpit already exhausted from consecutive flights, fully aware they were flying something unfinished. Engineers reviewed post-flight data, recognizing familiar deviations, but lacking the time to correct them properly. Factory workers on the assembly lines worked extended shifts, adjusting minor details within the limits of material shortages and immovable delivery schedules. Mistakes did not happen because of carelessness, but because the system forced human performance toward its limits. A bolt tightened slightly beyond specification, a decision to continue a takeoff for a few seconds longer, a report submitted with the quiet hope that next time will be better. No one had the authority to stop the entire process and begin again. Faces that appeared in accident files were quickly absorbed into statistics while the machinery continued to move forward. There are no heroes here in the conventional sense, only ordinary people placed inside a structure where individual choice was compressed between professional duty and relentless time pressure. And it was in that space that the cost of progress began to reveal itself with clarity. The cost did not arrive in a single moment. It accumulated flight by flight. Accidents occurred on American soil before a single bomb was dropped in combat. Failed takeoffs ended with shattered airframes at the edge of runways or crashes into nearby neighborhoods. Some test flights never returned, taking entire crews with them. Their names appeared in technical reports before they appeared in obituaries. The losses went beyond human life. Each destroyed aircraft represented thousands of labor hours, scarce strategic materials, and weeks of disrupted production. Every accident forced pauses, investigations, and hurried modifications, only to resume under even greater pressure. Emergency fixes made to address takeoff problems often introduced new issues later in flight. Engine overheating, unstable systems, unanswered questions about crew survivability. There is no moral judgment in these numbers. They simply reflect the reality of a system pushed into operation before it was ready. The price was paid in people, money, and time. Elements that never appear in design specifications yet always surface when a program is forced to move faster than its own limits allow. In the end, the program was not canceled. Runways were extended, procedures were revised. The aircraft's configuration slowly moved towards something that could be operated with acceptable risk. When it finally entered combat, it fulfilled the strategic role that had justified its existence: long range, heavy payload, and operation at altitudes difficult for the enemy to contest. But that outcome did not erase what came before it. Success arrived later than planned, and it rested on compromises that left lasting marks on design, operations, and doctrine. There was no moment of celebration in the technical records. Only dry annotations documenting what had been accepted, what had been deferred, and why the system could finally function. The result was not a clean victory, but a state of stability reached only after human endurance and infrastructure had been pushed to their limits. This story does not belong solely to World War II. It repeats itself whenever technological ambition moves faster than the infrastructure meant to support it. From modern aviation and next-generation weapons to global supply chains, the pattern remains the same. A system can be theoretically sound and still fail when placed into real operational conditions. When time becomes the decisive variable, temporary fixes inevitably emerge, not as optimal choices, but as the only choices left. The lesson is not about eliminating risk at all costs, but about understanding where that risk is transferred and to whom. When political urgency and schedules begin to override engineering limits, human beings inside the system become the buffer that absorbs error. Recognizing this does not make large projects easier, but it allows societies to better account for the true price of speed, pressure, and ambition. History is not decided by spectacular battles alone, but by the technical problems solved or left unresolved behind the scenes. And sometimes, what shapes the outcome is not the weapon itself, but the missing meters of runway and the people who paid the price for that absence.